Hello, my fellow upchuckers. My name is Clint Hoagland, and this is Creating Electronic Music with ChucK. In our last video, we looked at a new addition to the ChucK language, constructors, and we looked into how to use those and also how to integrate them into our own code. We also looked into another cool thing that got added a while back, which was how to access the documentation that is automatically included in ChucK objects. A big thing that got added in ChucK 1.5 was the inclusion of what ChucK calls CHI, which is the name of the way AI is integrated into ChucK. CHI seems really neat, and I'm looking forward to understanding it a little better and hopefully discussing it in future videos. However, it also seems like a big topic that I do not currently understand all that well, so let's take our first step toward understanding this part of the ChucK universe by taking a simple step forward and learning something simple first. Let's start learning about unit analyzers. We've spent a lot of time learning about UGens, which are the basic sonic building blocks in ChucK. UGens are essentially nodes in a sonic graph which get connected using the ChucK operator. Unit analyzers are cousins to UGens, and they are similar to UGens but have a different purpose and act a little differently. Terminology time. ChucK refers to a single unit analyzer as a yuana and more than one yuana as yuana, singular, yuana, plural, yuana. So the scope of this video is understanding how yuana are similar to UGens and also how they are different. That will set us up to understand some of the actual yuana types later on. In order to understand how yuana work, we're going to need to go into some detail about how data moves around in a ChucK program. As we've seen lots of times, the way you connect UGens together is by chucking one into another, like so. Chucking UGens into one another creates what we can call a ChucK graph, which is essentially a network where quote-unquote nodes are UGens, and the ChucK operator is how we create a quote-unquote edge connecting two nodes. Now, because of the way real-life cables work, and also because the ChucK operator looks like an arrow pointing from left to right, it's natural to assume that data gets pushed along this graph from left to right. However, that is not the case. What actually happens is this. When time advances, the DAC asks each node that is connected to it for samples to fill up that time. Each of those nodes will ask any nodes that are chucked into it for samples that it needs to satisfy that request. So let's say, for example, that we have a sine oscillator chucked into a reverb, which is chucked into a gain, which is chucked into the DAC. If time advances one sample, the DAC asks the gain what that sample's value is. The gain asks the reverb what the next sample is, and the reverb asks the sine oscillator what the next sample is. Each of those UGens is responding to a downstream request for a sample. If time advances 1 second, then it will ask for whatever number of samples per second is specified by the current sample rate, as in, if the sample rate is 44,100 Hertz, then it's going to ask for 44,100 samples every second, and that's what gets passed along from UGen to UGen along this graph. This is why, if you unchuck a UGen from the graph, it stops doing any work. Nobody's asking for its next sample, so it doesn't calculate it, and it just sits there doing nothing. And that is the reason why black hole exists. You may want a UGen to do its thing, even if it's not pumping audio into the DAC. Black hole asks for a sample as if it was a DAC. It just discards it, but a side effect is that the UGens that are upstream from black hole all get a request, so they do work when time advances. So, a way to perceive a ChucK graph is as a set of nodes connected by these lines we call edges. Audio samples get passed along edges when they are requested by nodes further along the graph. Now, the reason it's useful to think about this in this way is that UGens are one type of node which operate on audio samples, and the edges that connect them are connections where audio samples are being passed onward. A yuana is a different type of node that can also exist in a ChucK graph. They're a different kind of node that exists in ChucK. They don't necessarily input or output audio samples. They may also analyze audio samples and turn that analysis into what we can call analysis results. Or they may take analysis results and turn those into audio samples. What that means is there's going to be a kind of edge in our graph that is not an edge for passing audio samples around. There's a different type of edge that is for passing analysis results around. Let's say we have some kind of analysis we want to do on an audio file that's coming from a sound buffer. Let's not worry for now about what that analysis is or how to do it. Let's just focus for now on what would need to happen for that analysis to take place in our ChucK graph. We would need some kind of node that converts audio into results so that it can be passed along into one of these results edges, and then you would need a node that actually uses those results to do some kind of analysis. And that is how the ChucK language uses yuana. The converter node is a yuana, this analysis node is a yuana, and there's a special kind of edge that connects them to pass that analysis along. So how does this look in code? As we know, we can create one of these what we call audio edges using a ChucK operator. If I connect a sine osc to a DAC by a ChucK operator, then that creates an audio edge. What if I want to convert audio into an analysis and move over into using an analysis edge? Just like in our prior example, we're going to need a yuana that converts audio samples into analysis results. One such yuana is the FFT yuana. FFT stands for Fast Fourier Transform, and the yuana does exactly what we're saying. It transforms data from audio samples into analysis results. How does the Fast Fourier Transform work? Great question. Let's put a pin in that and save it for a future video since I only have a layperson's understanding of it and it seems like a deep topic. For now, let's just accept that an FFT takes in audio samples and puts out analysis results. Now we want to take those results and do something with them. To do that, we connect it to another yuana called a centroid. This connection, this edge, is for passing analysis results along, so it uses a different operator. This is called the ChucK operator. This is how you create a connection meant for passing analysis results instead of audio samples. We use the ChucK operator to connect the FFT to the centroid yuana. This creates what we called a results edge earlier. FFT turns audio samples into results and then passes them along as results to the centroid analyzer. You do still need either a DAC or a black hole at the end of this graph to pull samples through the system. So we wire, using the ChucK operator because the black hole asks for samples, the centroid to a black hole so that samples get pulled from the sine osc into the FFT, which then passes results into the centroid. Having wired all this up, we can now do analysis on the sound coming out of the sine oscillator. Now, the next thing we have to understand is that audio analysis cannot happen instantaneously. If you look at a sine wave in Audacity, that sine wave is composed of numerous samples that happen over time. If you were to look at a different sine wave at a different frequency, that would also be composed of different samples taking place over time. If you were to look at a sawtooth wave or a square wave, those two would be composed of many individual samples taking place back to back over some time period. If you zoom in and look at one particular sample, there is no way to know what kind of sound it is part of. The shape of a sound has to do with the relationship of samples to each other. You cannot learn much of anything about the nature of a sound by examining a single sample. You need a big enough batch of them such that you can see how the sound takes place across time. This means that a yuana doesn't just start emitting analysis as soon as any sample comes through its front door. Instead, you tell it when to do its analysis, and then it will reach back across the duration it needs to do its work. Then it will hold the results of its analysis until the next time it gets a request to do another analysis. To tell a yuana to do its analysis, you call that yuana's ChucK method. When that method gets called, the yuana does an analysis, stores the result inside itself in an object called a yuana blob, and then waits for further instructions. If a yuana needs upstream results in order to calculate results, like the centroid does, then it calls any yuanae that are upchucked into it to get those results. Thus, calling the upchuck method on a yuana that is connected to yuanae upstream from it will call the upchuck method on those yuanae as well. So in this particular ChucK graph, if we call the upchuck method on the centroid, then that will call the upchuck method on the FFT yuana because they are connected together. Okay, so let's see this working. According to Wikipedia, a centroid takes FFT data and computes the center of mass of a signal, whatever that means. Let's see what it spits out. Like I said earlier, if you call an upchuck method on a yuana, it will compute results on whatever batch of samples it needed to do that analysis, and then it will stash the result inside the object. Technically, it's sitting in an inner object called a yuana blob, but for this example, we don't need to care about that. You can get at the results directly by asking for members of the fval array. Let's print fval0 to the console. Now, I had to do some massaging of this script in order for this to give us results that make sense, which I did by stealing stuff from some examples in the examples directory. In order to get what seems like the understandable output for the centroid here, I multiply that fval by a second divided by a sample, which is the same thing as saying the sample rate, and then dividing that by 2. There's a couple of other things we need to do to make it work as well. We need to provide a buffer size to the FFT as well as a windowing. I don't know what that means exactly. I could make a guess, but let's just save that for when we dig into fast Fourier transforms. We also need to send some samples through the system before we call upchuck so that the FFT has something to analyze. With all that wired up, we can launch this script and we can see that it outputs something very close to 440, which is the frequency of our sine osc. So I'm inferring that to mean the centroid has successfully taken the results from the FFT yuana and calculated that the quote-unquote center of mass of that signal is what's in that sine wave. If we change the sine oscillator frequency to 880, then the centroid reports approximately 880. And if we try 220, it reports 220. So that seems like it's working. If we change the sine oscillator to a square oscillator, then it reports something much higher, which tells us that, according to a centroid, the center of mass for a square oscillator is not at its fundamental frequency, but at something much higher. I can't tell you right now with any confidence what that means or even if I am interpreting that correctly, but it does tell us that we now know how to wire up a couple of yuanae, and we know one way to read results out of one of them. Why is this interesting? There's a couple of ChucK technologies that have come online in the past couple of years that make it interesting. The first is that ChucK now has the capability of emitting computer graphics called ChucK. Theoretically, if we are able to analyze the sounds we are making in ChucK, we can also use them as an input into that graphics engine so that we can use sounds to control those graphics. The second is that, as mentioned earlier, there are new AI features in ChucK. The way that those work, as I understand it, is that we need to set up unit analyzers to feed data to ChucK such that it can train a local model to do machine learning. Obviously, all these are extensive topics that will need to be broken down into smaller chunks. For the purposes of this video, I think we accomplished what we set out to do. In this video, we learned about unit analyzers in ChucK, which we call UANA. We learned how they are different from regular UGens, we learned how to connect them up inside a ChucK graph, and we learned how to view the results of their analysis. In the next video, I want to try doing another finished composition since it seems like a fun thing to try while doing some background research on some of these deeper topics.